Draining water through a circular hole. A closed and elevated vertical cylinder tank with diameter D equals 2 meters contains water to a depth of h equals 0.8 meters. A worker accidentally pokes a circular hole with diameter d equals 0.02 meters in the bottom of the tank. As the water drains from the tank, compressed air above the water in the tank maintains a gauge pressure of delta P equals 5 times 10 to 3 pascals. It's a gauge pressure. Ignore any effects of viscosity. Part A. Just after the hole is made, what is the speed of the water as it emerges from the hole? What is the ratio of the speed to the efflux speed if the top of the tank is open to the air? Okay, so we're going to deal with part A in this video. Now we have this tank, elevated tank, which has a depth h. It's maintained at a gauge pressure delta P, so therefore the pressure here is atmospheric pressure P0 plus delta P. At the bottom of the tank we have a small hole with diameter D, which is open to atmospheric pressure because it's open to the ambient. And this is our coordinate system, x and y axis. And we can write Bernoulli's equation for this flow of water through this small hole. Now, if we start with the pressure on top, the pressure on top is P0 atmospheric pressure plus delta P, the gauge pressure. And then we have the potential energy term, the density of water, gravitational acceleration h, rho gh, and then we have the kinetic energy term. This top surface is moving, so we have plus 1 over 2 rho v top squared. This must be equal to the pressure at the bottom, outside pressure P0, plus we don't have any potential energy here because I'm taking this as the origin on the y-axis. So this is rho g0, potential energy term, plus because it's draining, we have a bottom speed 1/2 rho v bottom squared. This is Bernoulli equation. All right, so you can see that P0s will cancel here, and I will be left with the gauge pressure, delta P. So this will tell me that delta P plus rho gh is equal to 1 over 2 rho v bottom squared minus v top surface squared. Now, since the volume flow rate must be the same at the top and the bottom surfaces, we have a requirement that v top times area of the top surface. So this is area times dx, which is basically the flow rate, dv dt. This should be equal to the flow rate at the bottom, v bottom volume flow rate times a bottom, which is the efflux speed. So what is the area of the bottom surface? It is pi d over 2 radius squared. It's a circular hole, and we have a circular top surface which has diameter d, so therefore its area is pi capital D over 2 squared. All right, now remember that capital D, the diameter of the tank is 2 meters, and our circular hole has a diameter 0.0200 meters. Therefore, if you look at the squares, capital D square is much greater than D square. So we can say that if you look at the ratio of the speeds, so if I write V bottom divided by V top, according to this equation, the constant efflux rate, I have A top divided by A bottom. So this is the ratio of the top and bottom surface areas, and this is much greater than 1 because capital D is much greater than D. So you can see here. Therefore, what is the conclusion? The speed at the bottom, V bottom, is much greater than the speed at the top. So, what can we say about V top? It can be neglected. All right. So, if I go back to Bernoulli's equation, I have delta P plus rho GH is equal to 1 over 2 approximately, because I'm neglecting now V top, 1 over 2 rho V bottom squared. So this gives me the following result for V bottom, followed approximate result. It is 2 delta P divided by rho plus 2GH and square root. All right, so I multiply both sides by 2, 2 delta P, 2 rho GH, and divide by 2, 2 delta P over rho, and I obtain 2GH here, so it's in the square root. I have this symbolic result. Now I can substitute the numbers. Delta P was given in the problem statement as 5.00 times 10 to 3 pascals. The density of water is 1000 kilograms per meter cube. The depth of the tank height is 0.800 meters. Therefore, V bottom will be 2 delta P, so it's going to be 2 times 5 times 10 to 3 pascals divided by 1000 plus 2 gravitational acceleration 9.8 meters per second square, and height is 0.8 meters, and then we take the square root, and this gives us V bottom equals 5.07 meters per second. So that is with this gauge pressure. Now, if the top is open to air, what would happen? Then I would have no gauge pressure. Delta P would be 0 pascals. So I would obtain V bottom prime. Now, if you substitute delta P equals 0 here, this would become square root 2GH, which is the result for free fall, square root 2GH. And if I substitute the numbers, V bottom prime will be 9.8 times 0.8 square root, which will give me, for V bottom prime, 3.96 meters per second as my speed. Okay, so when the top is maintained at a higher pressure, I see that the speed with which the water drains through the circular hole is greater. All right, so in this part of the problem, first we have discussed Bernoulli's equation for this tank. The tank was closed and it was maintained at a gauge pressure delta P, which means the pressure on the top is P0 plus delta P. And we had a small hole with diameter D open to air, so atmospheric pressure P0 on the other side. And writing Bernoulli's equation, we have the pressure on top, P0 plus delta P, plus rho gh, potential energy term, plus 1/2 rho v top square, the speed with which this top surface comes down, is P0 plus rho g0, because that's y equals 0, plus 1/2 rho v bottom squared, the speed with which the water drains. And P0's cancel, and I obtained this equation. And then I noted that the volume flow rate on top and bottom should be the same. The volume flow rate is area multiplied by the speed. And equating these two and noting that the area on top is much greater than the area at the bottom, I see that the top speed can be neglected. So this is approximately 0. So I obtain this simple equation, delta P plus rho gh equals 1/2 rho v bottom square. And this gives me the answer I'm looking for. We can substitute the numbers to obtain 5.07 meters per second. What is the meaning of having this open to air? What is the ratio of the speed to the efflux speed if the top of the tank is open to the air? If the top of the tank is open to the air, then there is no delta P. Delta P is equal to 0, so I substitute 0 here. Square root 2gh is the answer, which tells me that the speed with which the water will drain will be less, about 1 meters per second less.